Hi guys, what's the crack? So what we're going to do now is we're going to look at simple harmonic motion. So one of the questions you can get in simple harmonic motion in your exam is how to draw displacement time graphs, velocity time graphs, and acceleration time graphs. So we're going to try this exam question about a mass and spring system, but just before we do, I want to make sure we're okay with what simple harmonic motion is. So simple harmonic motion, the conditions for simple harmonic motion is that the force is always going to be directly proportional to the displacement. Okay, so the force is directly proportional to displacement. And the other condition is that the force is always going to be towards the equilibrium. So what that means is the force is always going to end up being a restoring force. Okay, it wants to bring it back towards the equilibrium position. So that's why, because of these two conditions, we end up with the acceleration being directly proportional to negative of x being the displacement. So I just draw that in a graph. Acceleration is directly proportional to negative of the x. That's how you get your graph to look at this. So acceleration is directly proportional to negative of the x. So what we want to do is, again, we've imagined a spring and it's undergoing simple harmonic motion. So it means it's going to oscillate about its equilibrium position. So I'm going to mark on where its equilibrium position is. So that's going to be my x equals 0, its equilibrium position. It says the mass gets pulled down at distance a. So we're going to pull the mass down at distance a, so to this new point. So that's where my new mass is. And then what we're going to do, that's going to be our time equals 0. Okay? So the first thing I should look at displacement is that at time of 0, it's going to start at negative a, right? It's going to start below the equilibrium position. So when I start at negative a, that's my starting displacement. Once we let go of it, it's undergoing simple harmonic motion. So what it's going to do is going to oscillate from negative a up to positive a and back down to its equilibrium position. So if we're starting down here at negative a, what it's going to do is it's going to move up towards 0. So we know it's going to move up towards 0. Once it gets to 0 displacement, it's then going to go up further to positive a. So somewhere up positive a. Then once it gets to positive a, it's going to go back down to its equilibrium. And then once it gets back down to its equilibrium, it's going to go back down to where it started. So back down to my negative a. So hopefully, if you look at this graph, you can see that what's going to happen is going to be my cosine graph, but the negative cosine graph. So I'm probably just going to do that for 2 cycles. So I'm going to get a negative cosine graph. Now to think, how does the velocity look like compared to displacement? So for velocity, again, I think once being pulled down to this negative a, that maximum displacement in the opposite direction, its velocity is going to start at 0. And we know that because you think about projectile motion. It's the easy way to imagine it. If I was a person and I was to throw a ball up, I know when the ball goes up, what goes up must come back down. And at this maximum point here, when that ball changes direction, that's when its speed is 0. So again, here at our maximum, our extreme, when it's about to change direction, that's when our speed is 0. So we're going to start at a speed of 0. What's going to happen now, it's going to go upwards, okay? So it's moving the upward direction. So the speed right now is going to move it towards the positive end. So the speed is going to its maximum point, and it's going to the maximum point in the positive direction. So it's going to a maximum point in the positive direction. Once it gets here, it's then going to go up towards 0. So again, it's keeping the positive axis towards 0. And then now it's going back down towards my equilibrium again. So now the velocity is going in the downward direction, okay? Because remember it said we're taking up as positive. So anytime it's moving up, that's our positive numbers. And anytime it's moving down, that's going to be our negative numbers. So you can see here what we end up with is a sine curve. And I just want to make sure that it matches up. So I should make sure that these points align for my different parts of my cycle. So I'm probably going to squish it in a little bit more to make sure that my points are going to align for my full cycle. And then again, I'm just going to repeat it for 2 cycles. Okay. So next one then is my acceleration time graph. For my acceleration time graph, we can see that the easiest way to do it is always directly proportional to negative of the displacement. So if my displacement was a negative cosine graph, my acceleration is going to be the negative of that. It's going to be a positive cosine graph. So it's going to be my positive cosine graph, and we're going to do it for 2 cycles. Okay? Or if you want to think about the graph, at the start, when we were way down here, what we said is we're at the maximum negative displacement. the acceleration, the restoring force is towards equilibrium. So acceleration is in the upwards direction towards equilibrium. So my acceleration is a maximum here. When it gets to this point, that's when the acceleration becomes 0. When it gets to this point, again, the acceleration now is trying to pull it in the negative direction down. It's going to be a maximum. And when it gets to this point, again, my acceleration is 0. And then we get back to where we started. Our acceleration now is trying to pull it upwards towards its equilibrium position. So these are my 3 cycles for displacement time, velocity time, and acceleration time graph. So if you find it useful, just remember to subscribe to get more videos and hit the bell icon to get the notifications. And just share it with your friends to make sure you all can get access to these free resources.